Hello, George Romanic here. In my previous video we investigated the first Fick's law, or the law of self-diffusion, but when the conditions are steady state. The question is, how do we generalize first Fick's law to transient conditions, namely when we do not have steady state assumption? That is what we are going to investigate in today's video, and that is known as the second Fick's law. Before we go to the mathematics, I would like to ask you to share this video so that more people is aware of this channel and these videos. With that being said, let's get started. Consider an ideal gas with a lot of particles moving in any given direction, just as we always have that in these types of videos. And now, in this gas, like in my previous video, I will introduce tracer particles, which I paint in red. And you will see that the way I'm plotting this, there will be a gradient in the concentration of these red particles from the bottom of this figure towards the top. In other words, there will be less particles at the top compared to the bottom. Furthermore, I will introduce this to be my z-axis. And what we want to investigate today is the following issue. Imagine I introduce two layers in this gas, and they can be these two layers. At the height z, this one, and this one is at the height z plus dz. In this video, we want to know how diffusion changes with time. To do that, we will introduce a volume over here. So let's say that this goes into the page. Suppose that the area of this box is unit area, just like in our previous video, and therefore this is also unit area over here. We want to know how the number of red particles is changing in this volume with time. Well, like in previous video, we define nt, which is clearly a function of z, as the number density of these red particles, and that is basically total number of red particles, tracer particles, in volume V. Now this volume V is not volume of this box, but volume of the entire space where this box is located, whatever that is. Anyways, we define this as the number density of tracer particles, and that's defined per unit volume. But I want to know how many tracer particles is in this critical volume over here, and that would clearly be nt, which is function of z, times this volume. But this volume has surface 1, namely 1 times height dz. So this is nt of z dz. And as I said, we want to find change of this number with time. So I need to differentiate this with time. So that means that delta nt, which is function of z and also function of time, delta t times dz is equal to what? Well, it's equal to flux of these particles in our volume minus flux of these particles out of the volume. Some of you might say, but why did you define this as flux in minus flux out? Why not the other way around? Well, looking at this picture, if flux of the red particles into the volume is larger than the flux out, then this will be larger than that, and that means this will be positive, and therefore this will be positive, which means that the number of red particles in this volume is increasing with time, and that makes sense. On the other hand, if this flux out of the volume is larger than the flux in. That means more red particles is leaving my volume, and that means this is larger than that, which means this becomes negative, and that means that this becomes negative, and that makes sense because the number of red particles is decreasing with time in my control volume. Also, when I differentiate this with respect to time, I don't differentiate this because this volume is not changing with time, so dz is constant. Now, in my previous video, as I said, I spent almost 2 hours demonstrating that flux in is jd at this height z and time t, and flux out is jd at this height z plus dz and time t, where d stands for diffusion, and this is flux of particles through these unitary areas. Now, as we always do in these types of situations, we will here express particle flux at the top surface by using particle flux at the bottom surface and using Taylor series expansion. Namely, jd at the height z plus dz and time t will be jd at the bottom surface z and time t plus a rate of change of flux along my axis z times the distance dz, and of course plus hot, higher order terms. But we neglect higher order terms as usual, because in this case we assume that these fluxes are not profoundly different. From here we can see that jd at the surface z plus dz and time t minus this jd at the surface z and time t is simply equal delta jd delta z times dz. And now I can substitute this expression over here, and I will get that delta nt at height z and time t, delta t times dz is equal, you will notice that this expression is negative of this expression, so that will be negative delta jd delta z times dz. dz and dz cancels. From my previous video we explicitly derived that jd is equal negative d times delta nt delta z. This is Fick's first law of diffusion, and this d is a constant known as constant of self-diffusion. You remember it is equal mean speed of atoms in a gas times mean free path divided by 3. Now, substituting this over here, we can see that delta nt delta t, I will omit now this functional dependency for shortness, is equal negative delta delta z, jd is negative d delta nt delta z. Minus and minus will cancel, and we get that delta nt delta t is equal delta delta z of d delta nt delta z. And this is a very beautiful result. So we can see, first of all, that if d has dependency on z height, we cannot move it in front of the differentiation. We could ask ourselves, is it possible that d can be function of z? And the answer is yes, of course, very much. Because d is mean speed of atoms in a gas times this mean free path. And you will remember from my previous video that these quantities depend on temperature and pressure of the gas. And particularly, we discussed in my previous video that this d, coefficient of self-diffusion, is proportional to absolute temperature to power 3/2 and inversely proportional to the pressure of the gas. So that means if this gas is not in temperature equilibrium, maybe here is hotter than here, then this is not constant in respect to height, and we cannot take this out of differentiation. Similarly, if the pressures are different along this z-axis, once more there is dependency of d on z, and we cannot take it in front of differentiation. However, in most cases, we are looking into the gas that is in equilibrium, thermal equilibrium, which means d is indeed constant, and in that case, we can take this out of the differentiation, and we get that delta nt, delta t, is equal d delta second nt delta z squared. And this, ladies and gentlemen, is known as second Fick's law. Of course, there is absolutely nothing special in terms of our z-axis. I could set up this situation in terms of x or y-axis, and therefore we can generalize this law to be delta nt delta t is equal d delta second nt delta x squared plus delta second nt delta y squared and plus delta second nt delta z squared. Or we could write this as d nabla squared Laplacian of nt. This, what we just derived, is the second Fick's law. What it tells us is how diffusion changes with time if the fluxes of particles are changing with time. Very important concept. The video is not that difficult if you properly understood concepts introduced in the previous video, and these concepts are not necessarily so simple. As I discussed in previous video, they are simple qualitatively, but when we want to describe them using rigorous mathematical methods, that becomes a little bit tricky. However, I went into great lengths in my previous video to demonstrate all steps in the simplest possible way. So if something was not clear here, I suggest you check my previous video, and I believe both first Fick's law and second Fick's law will be clear to you. Until next video, goodbye.